Differential equation. This is the fourth FRQ. It's a non-calculator FRQ. Consider the differential equation dy dx equals y minus 2 times x squared plus 1. There are three questions. Question A is find y equals g of x, the particular solution to the given differential equation with initial condition g of 0 equals 5. That's an obvious question if we have a differential equation FRQ, and as I said several times, these questions earn a lot of points. If you can find the particular solution, it's 4 or 5 points very easily. So student A went through these steps. First of all, they separated the variables, so the y's with dy's, the x's with dx. That's the first step you need to do. Secondly, the student added the integral signs on both sides, and then they integrated. So the integral of 1 over y minus 2 dy is ln of absolute value of y minus 2, and the integral of x squared plus 1 dx is 1/3 x cubed plus x plus c. From here, the student proceeded with trying to find the value of c. So to do that, we have the initial condition x equals 0, y equals 5. So you plug in y equals 5, x equals 0, and you end up with ln of 5 minus 2 equals 0 plus c. Therefore, c equals ln of the absolute value of 3. But that means ln of 3 because it's a positive number. So back here, the student plugged in c equals ln of 3 and continued to solve. Now in this step, I want to discuss a little technical difficulty. The student gives no explanation about how they got rid of the absolute value, and it's not always obvious. In this case, the student was lucky. There are cases where AP will purposefully choose the negative case, and if you don't know exactly what you're doing, you're going to drop a point. So from this line to this line, of course, we take the exponential on both sides, but we should still have absolute value of y minus 2, which means it's either y minus 2 or 2 minus y. And how do we choose, how do we figure out which one it is? Well, you know that when x equals 0, y has to be equal to 5. So if you plug in x equals 0 here, as you know, you will always get a positive value for exponential functions. So this is positive. It has to be 5 minus 2. It can't be 2 minus 5. So indeed, it is this, just like the student did. You can discard this answer. Now, why is it not both is something I will talk about in a minute when we check the graph. Anyway, just reaching the answer, adding 2 on both sides, y equals 2 plus e to the power of etc. You want to do that for the following reason. It's written up here that we want to find y equal. So we want to find y explicitly as a function of x. All the x's are here and the y is on the left. Well, it's on its own side. So you can't stop before you really reach y equal an expression of x. So I know it's not a calculator exercise, but this situation happens a lot when you have ln of absolute values of expressions, and it's always basically the same thing. If you keep both the y minus 2 and 2 minus y, it opens up a case like that, where for each x value, I have 2 values of y that are possible. And that's not a function. We always want to find a function, so when I have one x input, there will only be one y output, not 2. So in this graph, the red graph is y minus 2 equals e power etc. And the blue graph is the graph of 2 minus y equals e power etc. So which one goes through the initial condition x equals 0, y equals 5, it's the red graph here. This is the initial condition, so we want it to go through that point, so we discard the blue graph. Points: 1 point for separating the variable, 1 point for each integral, 1 point for finding the constant of integration, and 1 point for reaching y equal explicitly. Nice work, even though there's a little ambiguity here, and the second student will do a much better job of showing his work or her work in this particular case. So student B, dy dx equals y minus 2 times x squared plus 1. In one step, the student separates the variable and then adds the integral signs. And when the student integrates, they find ln of y minus 2 with absolute values equals 1/3 x cubed plus x plus c. That's great. Crossing the c here is not exactly correct, but I mean, we probably can follow what the student did. So when the student takes the exponential, it becomes y minus 2 equals e power 1/3 x cubed plus x plus c. And now using the property of exponential, this is e power 1/3 x cubed plus x times e power c, and the student decides to call this new variable a. In class, we've often called this new variable capital C. I actually find it much nicer to use capital A. It's less confusing. And here what the student does is really great. They say a can be plus or minus e to the c, and therefore this is how the student gets rid of the absolute value. So notice the difference. The student solves for y first, y equals a times e, etc., and then searches the value of the constant a. And in that way, the student manages to get rid of the absolute value somewhat more easily than the previous student, and more correctly too. At this point, the student found y equal, and they want to find the value of a for the particular solution, so they plug in x equals 0, y equals 5, and this is what the student gets. A equals 3, this is correct, well done. But unfortunately, when writing the final answer, the student forgot to add the plus 2 in the end. So 1 point for separating the variable, 1 point for each integral, 1 point for finding the constant, and 0 points because of this tiny mistake. It's very sad, and we'll see it'll have more consequences. Student 3 separated the variables correctly here, even though here you really want to put parentheses just to avoid any ambiguity. And then when integrating, the student got confused, somehow thought they could integrate the denominator on its own, but this is not correct. This should be ln of the absolute value of y minus 2. On this side, the student integrated correctly, so they earned a point for that. Now the sad news is part of the assessment in this question was to see how students handled logarithmic and exponential expressions. And because the student does not have any log or exponential, from here on there was no point to be earned anymore. And we won't go into the details of what the student did because it doesn't really matter. So 1 point for separating the variable, 1 point for the first integral, and then no point for the other integral. And I'm sorry, apparently the student earned 1 point for finding the correct constant. So 0 points for the final step. This is, I guess, what I wanted to say. The question was expecting student to handle a log and an exponential and making decision about the absolute value, and since this cannot be the case because of the student's mistake, even though this work may be perfectly correct, we can't count the last point. It's nice to see that they earned a point for the constant though, so graders are careful and they do their best, I guess, to find points. Question B, find the limit as x approaches negative infinity of g of x that you found in part A. So in a question like that, they don't ask for justification, they don't ask for work, they will only be looking for the answer. So what happens if x becomes extremely negative? E power, a very negative number, will approach 0, so the limit is 2 plus 0, and that is equal to 2. This is well written. Student B was missing a +2 from the previous exercise, and we notice here that they would have done the exercise perfectly. There's a +2 here, it should be +2 here, it should be 3 times 0 +2, and they should find 2. In this case, the graders did not care much and just gave 0 points. So it's such a tiny mistake in question A, and it has the consequence are 2 points are dropped. Student C didn't understand the problem. Maybe they just tried. Maybe they thought, maybe it's because of their function in question A. It might be the correct answer for the function they have in question A, but as for student B, they didn't earn any point. Finally, question C introduces a new particular solution. This time we are looking for a function f of x such that the initial condition is f of 1 equals 3. So we could redo exercise A again and find another function that would also fit the differential equation, but it would go through the point 1, 3 instead of 0, 5. I did it, and we'll see the graph in a minute. But the question is, find the value of the second derivative at the point 1, 3, and then answer the question, is the graph y equals f of x concave up or concave down at that point? Give a reason for your answer. So the first part is very clear. Find the value of the second derivative. So we start with the first derivative that we are given, and using the product rule, we will take the second derivative. So d squared y dx squared equals y minus 2 times 2x plus x squared plus 1 times y prime. This is u prime v plus uv prime. And from this step, y prime, we substitute what we have up here. Y prime is y minus 2 times x squared plus 1. And we get to this expression here, where all we have to do is plug in x equals 1 and y equals 3. A few steps further, we find the answer. The second derivative at the point 1, 3 is equal to 6. This is a very nice work by this student. Conclusion, since the second derivative is positive, the graph is concave up. Perfect. In the solution provided by AP, they comment that the second derivative has to be greater than 0 and continuous, but that's really an extremely minor detail. They can't really expect us to add this comment. So if you solve for that particular equation, this is the function you would find, or maybe y equals this plus 2, and look at the graph. It's placed differently from the original graph we had earlier. This green graph goes through the point 1, 3. And we can see, of course, that it's concave up. It's curved. It's turning to the left. Let's have a look at student B. They start correctly by trying to find the second derivative using the product rule. U prime v, well, it's u v prime plus v u prime. I would recommend you always stick to u prime v plus uv prime. And from here, the student starts getting on the wrong path. They distribute, which is not a bad idea, but what they do that is really wrong is setting up the second derivative equals 0. This is an absurd decision because the question is, what is the second derivative? So if you set it up equal to 0, then you've just decided what the answer is, and it's not going to be 0. If you set up second derivative equals 0, that means you're looking for places where we have points of inflection. We're looking for places where the concavity is neither up nor down. So from here on, there was no chance that the student would get the right answer. In the end, they find dy dx equals -1, but how could that be correct since that's not the question? We need to find d squared y dx squared equals something. The conclusion also doesn't make a lot of sense. The graph of y equals f of x is concave down because the second derivative is 0. This seems like it has meaning, and it's usually correct. If the second derivative is 0, then the graph is concave down. But why are we talking about the second derivative at x equals 0? The question is, what is the concavity at x equals 1? So this is completely unrelated. Last student once again dropped points because of not assessing the standard. When they try to find the second derivative, u prime v plus uv prime, the derivative of y is y prime. It's not 1. And since a y prime is missing, the graders can't really assess the problems that were expected to be assessed in this question. So there was no way the student was going to earn points. It's difficult to manage this y prime. You had to plug in this a second time, as you saw student A do, for example. And because there's not even a chance this is going to happen, the student would not earn any points. Everything else the student does is a bit confusing, and I think it's better not to talk about it. In fact, it looks like the student is using the second derivative test. This is what I read here, second derivative test. That's completely unrelated, again, just like student B doing things that are unrelated. When do you do the second derivative test? You do the second derivative test when you've identified a place where there's a maximum or a minimum. And by figuring out if that particular point has a concavity up or a concavity that's down, you can say whether it's a max or a min. But there's no reason, there's no sense in taking the second derivative test if you haven't found points that could be min or max. So that's it for this FRQ, and I hope it helped. Thank you very much.